a very inspiring venue. Yes, I'd like to thank the organizers for putting it together, because really it's a lot of work. So we've heard already a few talks about erasure noise and how to correct it. Now we are all experts how to correct erasure. So if you erase my talk, you will be able to recover the information. So anyway, this talk is about two papers, and I would like to acknowledge my amazing collaborators from Amazon, Arbel, Haim, Yotam, Vaknin, Harry Levine, Fernando, Brandao, and Retzker. And in particular, I would like to acknowledge Harry, who was leading the experimental efforts. And of course, it goes without saying that our experimental results wouldn't be possible without the whole team at the AWS Center for Quantum Computing. We're at the QEC conference. We all want to build fault-tolerant quantum computers. And a typical path to fault tolerance is as follows. We have some physical systems, for instance, superconducting circuits and native operations that we can implement there. And then, of course, those qubits, those operations are not ideal, but we can improve them. And if they're sufficiently good, that we can start playing all the tricks from quantum error correction and fault tolerance. We can engineer logical qubits, logical gates of very good quality. And if we have them, we can abstract from the hardware and just run a quantum algorithm, our favorite quantum algorithm, for instance, Shor's algorithm. But it is important, I know that I'm preaching to the crowd, but it's important to realize that practical algorithms require billions of basic operations. So the error rates that we need to get are of the order of 10 to the minus 10 or even lower. And we do not believe that we can achieve such low error rates without quantum error correction. Unfortunately, there is the overhead of quantum error correction, and we all are working on reducing it. We heard talks on good LDPC codes that are trying to reduce the space overhead. We heard talks about single-shot quantum error correction that are trying to reduce time overhead. But it's a tough problem. We all know that, and the difficulty comes from the fact that it's a multifaceted problem. Finding good codes is not the final answer. We need to know how to operate on those codes. We need to know how to do logical gates. And then we also need to be able to experimentally realize those codes. And we have to operate within certain hardware constraints. And what I would like to talk about in this talk is that thinking about constraints imposed by hardware can help us to tailor quantum codes and lead to the reduced overhead of quantum error correction. So in this talk, we'll be thinking about how to reduce the overhead of quantum error correction. This is a very timely question to think of. And we will be taking a perspective of thinking about quantum error correcting protocols and codes that can be realized with currently available hardware. And I hope that it will be obvious that thinking about digging a little bit deeper and thinking about our system, it can really pay off. We shouldn't be assuming that we just have qubits and Pauli noise. We should dig a little bit deeper. So here's the outline of my talk. I will be very brief, but I'll just show you the decoding problem in the context of the toric code and bias noise. And then I will tell you about erasure qubits. It's a very simple idea where we want to leverage erasure noise. And then in a few slides, I will also tell you about our experiment with superconducting circuits. So let's get started. The decoding problem, we all know what it is about. It's important to remind ourselves that if we cannot efficiently solve it, we most likely will fail at building fault-tolerant quantum computers. So the decoding problem in general, for generic stabilizer codes, is computationally hard. But if we impose some structure, then we can efficiently solve it. And here's where the toric code comes into play. The toric code can be defined on the square lattice. Qubits are on edges. We have X parity checks associated with vertices, Z parity checks associated with plaquettes. Everyone in this room knows it. this is a CSS code. We can correct X and Z errors independently. So let's just focus on Z errors. And why am I showing to you the Torah code? Well, it's a very nice quantum error correcting code. It constitutes a backbone of many architectures to build quantum computers. But there's also a very nice cartoon illustrating how quantum error correction works with the Torah code. So we can think of errors as string-like objects, and then those errors, their signature will be the violated party checks that are located at the endpoints of those strings. And you can think of those endpoints as point-like excitations. And in the context of Floquet codes, we may see a very interesting physics story. But I will focus on the decoding problem, right? So we see the endpoints of the strings. We need to find appropriate strings. We need to pair up those point-like excitations. And we can make mistakes. We know how to solve the problem efficiently. This is our beloved minimum wave perfect matching decoder. And as we heard in the talk earlier today, the minimum wave perfect matching decoder, or some modifications of the minimum wave perfect matching decoder, are not only visually pleasing, mathematically pleasing, but they have practical ramifications. They are used, for instance, in the Google experiment where they scale up the surface code. So far, I was just talking about noise without any structure, but we may have some noise bias in the system. So for instance, for concreteness, we may think of a biased Pauli noise, where Z errors are more frequent than X and Y errors, and such systems can be engineered with, for instance, bosonic qubits. And then, if we have bias preserving gates, we can try to leverage the bias present in the system. So, the question is, can we do some simple tweaks to leverage bias? We don't want to redesign our quantum computing stack. We don't want to come up with a vastly different quantum error correcting code, because then we would need to do different decoders. We would need to rearrange our hardware and whatnot. It could be a lot of headache. So can we leverage bias? The answer to that question is yes. So in the context of the Torah code, if we think about this Z error, we notice that Z parity checks are insensitive to the dominant noise. So the very simple idea that originated here in Sydney is, what if we, instead of measuring Z parity checks, what if we measure Y parity checks? Well, then we will have more signature of the Z string-like error, and it turns out that we can leverage this information. And those ideas led to the very famous XZZX surface code, and a general realization of this idea is that if we have some quantum error correcting code, we can actually apply a Clifford operation locally to modify the structure of the code and adjust it to the bias of the noise. So you may ask, does this really help us? And yeah, you can check it, for instance, with the 3x3 surface code. And if you have some bias, and so what I'm plotting here is, I'm plotting different realizations of the 3x3 surface code, and they are all obtained from the basic one by applying single qubit Clifford rotations at different qubits. And what I can do is I can check what is the logical error rate of those codes. This is code capacity. This is in the context of code capacity. And we can see that the best performing and the worst performing codes, they can differ by 2 orders of magnitude. So even with those very small, benign tweaks, we can get a lot of performance improvement. So an obvious question is, this is the Pauli noise bias, but can there be other noise bias? And this is how we arrived at this idea of erasure qubits. So one of the noise bias that is pretty frequent in quantum technologies is the bias between the amplitude damping noise and the dephasing noise. So typically T1 is smaller than T phi. So what is the amplitude damping noise? Often a qubit is realized by choosing two states that correspond to different energy levels. So the amplitude damping noise models some process, a relaxation process from the excited state to the ground state that happens with probability gamma. And if you want to think about a channel, you know, I listed two Krauss operators that describe the amplitude damping noise. It turns out that amplitude damping noise can be corrected more efficiently than, say, the Pauli noise, the depolarizing noise. And this is exemplified by the example of the 4-qubit code that can correct, here there's a caveat approximately, one amplitude decay, amplitude damping error. Also, and if we want to correct an arbitrary Pauli error, we would need a 5-qubit code. Also, when we think about the surface code threshold for the amplitude damping noise, in the code capacity scenario, we could get almost 40%. For the depolarizing noise, we would get only 19%. So indeed, those are those two observations motivate or give us confidence that we may be able to leverage amplitude damping noise for improving the performance of quantum error correcting protocols. But how can we do that? Well, it turns out that there's a very simple dual rail encoding that can be used. So what is it? Well, we take 2 qubits and we define the effective qubit as the subspace spanned by state 0, 1, and 1, 0. And then if there is the amplitude damping noise that affects both qubits, then we can immediately write that with probability 1 minus gamma, if we act on the encoded state, nothing happens. And with probability gamma, the encoded state is mapped to the state 0, 0. Here, importantly, the state 0, 0 is orthogonal to the qubit subspace, so it can be detected. So this is basically the definition of erasure noise. And the dual rail encoding is an idea, is a realization of a more general idea, which is the idea of erasure qubits. So here we're thinking of defining our qubit in a way that the effective noise that affects that qubit is biased toward erasures. And we've heard during this conference that this idea can be realized with neutral atoms, trapped ions. I'll be talking about superconducting circuits, but I'm not particularly tied to any experimental realization. So let's see very quickly that correcting erasures is simple. Let's look back at the toric code. So I depicted here in thick gray edges the locations of erasures. For simplicity, we can think of that at those locations we replace the qubit state with the maximally mixed state. So this can be modeled as applying a single qubit Pauli operator at each location which is erased, and we choose this Pauli operator uniformly at random. So now what we will see is we will make some measurements. For instance, we will measure the X parity checks, and any valid syndrome, we can get any valid syndrome that is adjacent to the locations of the erased qubits. So how do we correct? We can do, for instance, Gaussian elimination, or we can find connected components and move all point-like excitations to one point within the connected component. It doesn't matter what exactly you do. You would be able to correct it without introducing a logical operator. However, if we didn't have the information about which qubits got erased, and you just applied minimum wave perfect matching decoder, for instance, you may be tempted to, so yeah, this is the correct correction, but with, say, minimum wave perfect matching decoder, you may arrive at the incorrect recovery operator. So it turns out that erasures can lead to extremely high thresholds. This can be seen by mapping the decoding problem for the toric code to a bond percolation threshold problem on n square lattice, and that's how we arrive at the threshold of 50%. Here, so far I was talking about erasures, but we can sprinkle some Pauli errors, and it turns out that we can immediately apply the tools that I briefly discussed to that problem too. You have the minimum paper matching decoder with adjusted edge weights, or you use the union find decoder, and it all works well, and we can correct errors. And with those decoders, then we can study what is the correctable region within the EP plane, where E denotes the erasure rate and P denotes the Pauli rate. And so the y-intercept on this plot corresponds to the threshold of the minimum prefer matching decoder for the phase flip noise. The x-intercept corresponds to the 50% threshold of pure erasures. And if we're in the correctable region, we can just scale the system up and get a better and better logical error rate. So in our work, we also looked at the sub-threshold scaling. So what we actually did is we simulated the memory threshold of the surface code against the standard circuit noise. And that happened with probability. The errors happen in the standard circuit noise with probability P. And on top of that, we also added erasures. We assume that each CNOT gate can erase both qubits with probability E, and we know when this happens. So in order to compare the erasure scheme with the standard scheme, what we need to do is we need to forget the information about the erasures. This will boil down to increasing the infidelity of CNOT gates. And then what we can do is we can again look at the EP plane and ask what is the correctable region. The dark color denotes the correctable region for the standard approach. The light color denotes the correctable region for the erasure scheme. And we see that we can increase the correctable region by a factor of 3.5. So that's all good. But so far I was telling you about perfect knowledge about erasures. This is not realistic. So we have to take into account false positive and false negative erasure detection. So false positive seems to be more detrimental because we will be the ones erasing our qubits. False negative are less detrimental because they basically boil down to increasing the Pauli error rate. But the Pauli error, it has to be like Q minus times E. So that's a small value. So, okay. So what is the take-home message from this slide? I'm just showing you some numerics, but the take-home message is that the target noise rates that we should be able to achieve in order to benefit from this scheme is the erasure rate should be of the order of 1%, the Pauli error rate should be of the order of 0.1%, and the measurement error rate should be of the order of 1%. This is our rule of thumb, and we will see that we can achieve those rates. Right, so we can compare, the different values of Pauli error rate, erasure rate, and measurement error rate. We can see how the logical performance behaves. We see that erasure scheme can outperform the standard scheme, even if the standard scheme has better fidelities. And at this point, you can be, wait a second. For your erasure scheme, you need more transmons, right? So indeed, to realize a dual rail qubit, we need two transmons, and in a standard scheme, we just have one transmon. But we expect to be able to use one readout resonator, and in the standard scheme, we also need one readout resonator. But when it comes to the actual chip size, the erasure scheme, we expect it to be only moderately increased compared to the standard scheme because transmons are small. And when we have erasure scheme, we can correct if we have n transmons. We ask a question: we have n transmons. What do we do? So with the erasure scheme, we can have the surface code threshold of root n over 4 by root n over 4, and so we can get smaller size surface code compared to the standard scheme. But we can correct more erasure errors than we can correct unknown Paulis. So what's the take-home message from this slide? Well, with the erasure scheme, we can gain in two ways. So first, we increase the threshold, the error correction threshold, because the threshold for erasures is higher than threshold for for the Paulis, and in addition, the exponent in the scaling of the logical error rate with the erasure scheme is higher than for the standard scheme where we have unknown Paulis. So at this point, I hope that I convinced you about the usefulness of the idea of erasure qubits. So now let's think about the experimental realization a bit. A natural platform to realize erasure qubits is neutral atoms, and this is the approach taken by the group at Princeton. But we can also have erasure qubits, for instance, with superconducting circuits. So we can take coupled microwave cavities. This is the approach taken by the group at Yale. Or we can have two resonantly coupled transmons. This is the approach that we're taking. We can also have trapped ions, as we heard in the earlier talk. So there is plenty of possible realizations of the idea of erasure qubits. So in our setting, the key idea is that the amplitude damping noise results in detectable leakage. So when I think about erasure qubits, and leakage, you can think of errors as detectable leakage. So in order to benefit from erasure qubits, we need to have a system where we can have a large erasure noise bias and the ability to detect erasure errors without disturbing our qubits. And in our experiment, we demonstrated that erasure qubits via the dual rail encoding can meet both of those requirements. So in order to show that we have a large erasure bias, what we did is we implemented single qubit randomized benchmarking intertwined with frequent erasure checks, as depicted in the diagram here. And what we saw is that the erasure rate was around 4 × 10⁻³ per Clifford gate. Post-selecting on no erasure events, my slide got erased. Sorry for that. Where were we? So we need to demonstrate the large erasure bias We did it by using the single qubit randomized benchmarking. We see error rate 0.4%. And when we post-select on no erasures, we see the residual error rate within the qubit subspace to be of the order of 10 to the minus 4. So we show that there's a large bias of around 40. In order to establish the ability to detect erasures without disturbing the qubit, we first looked at false positive and false negative detection events. So what we do is we prepare the state of the dual rail qubit either in 0, 0 or in the qubit subspace, and then we do a single erasure check, and then we measure the state of the dual rail qubit, and we saw that false positive and false negative rates are around 1%. And lastly, we want to also see that the phasing of the dual rail qubit due to erasure checks is pretty small. So what we were doing is we were evolving our dual rail qubit for some fixed amount of time, and at equal times we were performing erasure checks. And we saw that the phasing is below 10 to the minus 3. So if we compare to this to a previous slide, we see that the performance with the dual rail qubit is already compatible with the QEC targets that we need to be able to benefit from the erasure qubit. So let me make a couple of comments. So first, the features of the dual rail encoding, which is a large erasure bias and the ability to perform high fidelity erasure checks, is not fine-tuned. So here we can operate over a broad tunable range, and this provides advantages over the standard architectures where tunable transmons are expected to operate close to the sweet spot, flux insensitive sweet spot. And this ability to operate over a broad range can allow us to avoid, for instance, unwanted TLSs. So still, there's stuff to be experimentally demonstrated. For instance, we need to show that we can reset the erased qubit and that we can perform bias preserving to qubit gates. Here, I was talking about superconducting circuits, or was thinking about superconducting circuits, but those ideas are broadly applicable across different hardwares, as we've heard already. But what we need to have in each and every hardware to benefit from erasure qubits is first, large erasure bias, second, the ability to perform erasure checks without disturbing the qubit, and third, to have bias preserving gates. Again, in the talk, I was telling you and illustrating it with the idea of erasure qubits with the surface code, with the toric code, but other QEC codes can benefit from this idea. We can take some good LDPC code, and for sure the improvement, the performance will improve. And lastly, there's plenty of room for a thorough optimization. So in our considerations, we need to be more careful with how we model erasure checks. They are not for free. They take some time. They introduce further errors. So for sure, there will be some sweet spot when it comes to how frequently we should perform erasure checks. And again, here I was not showing any optimization where we take into account maybe soft information. This definitely would boost the performance of those protocols. So with that, I would like to conclude my talk. So I hope that I convinced you that thinking about hardware realizations of quantum error correcting codes can help us with reducing the overhead of quantum error correction. We should, we should not just think of qubits and Pauli noise. We should think about, we should dig a little bit deeper. And a realization of this mindset, erasure qubits, we arrived at the idea of erasure qubits via this path. And again, erasure qubits, as you know, is this simple idea. Let's convert quantum noise into erasure noise. That is fairly classical and therefore easier to correct. And yeah, it seems that those ideas are good ideas to realize hardware efficient quantum error correction. And as I showed to you, with superconducting dual rail encoding, we may be able to fairly straightforwardly realize those ideas. And with that, I would like to thank you.
We'll take 2 questions for Alex due to the technical difficulties.
Thanks for the nice talk. So your paper on this also had another proposal for using the GF states of the transmon. Can you comment on whether you think that is also implementable and why you did the dual rail instead?
Yes, so there was the GF qubit as well, but I think that it's better to do the dual rail encoding. It seems more streamlined. Yeah.
Any other questions for Alex? All right, then we'll get back on schedule. Thanks, Alex.
Thank you.